All right, everyone. I'm Sam Charrington, founder of TWiML. And for this Solutions Guide Spotlight video, we're going to dig into Run.ai with Guy Salton, who's a solutions engineering lead at the company. Guy, let's start with some brief background. What is Run.ai?
Sure, thanks, Sam. So Run.ai is a centralized compute management platform for the AI era. It helps make data scientists more productive by automating the provisioning and allocation of GPUs to the researchers' jobs, as well as help improve GPU utilization due to this capability and more.
Awesome. So let's jump in, bring it up, and let's see what it looks like.
Of course. So yeah,
what are we looking at here?
Yeah, so what you see on my screen right now is the Run.ai admin user interface. And here I can see a cluster, Kubernetes cluster with 2 nodes, yeah, and a total of 4 GPUs. So I have 2 nodes and each of them has 2 GPUs in it, so a total of 4 GPUs. I can see that out of the 4 GPUs, 1 of the GPUs is allocated to a job, right? I have 1 job running here. It's a train job, so it's training some deep learning model. It allocated 1 GPU and it's fully utilizing this GPU. And thus I see that the total GPU utilization in the cluster is around 25%, right? Because we're using 1 out of the 4 GPUs. So we give the admins visibility of what's happening in the cluster, right? Which jobs are running, what's the current GPU utilization, etc.
Got it. And right off the bat, you are mentioning Kubernetes. So Run.ai is a native Kubernetes solution. Is that the primary deployment environment that your customers use?
Correct. So, we saw that in recent years, the AI ecosystem is adopting containers for all the popular frameworks, and Kubernetes is now, de facto the new standard for container orchestration. So we decided to build our own scheduler for Kubernetes, because the default scheduler that Kubernetes comes with was not built for deep learning and AI. It lacks a lot of capabilities that are required for deep learning workloads. So what we did is we built our own scheduler for Kubernetes to support specifically deep learning and AI use cases.
And one of the things that differentiates deep learning and AI from the traditional workloads of Kubernetes web applications is the requirement to use GPUs, which are for many teams that are operating at scale, the precious resource. So how does Run.ai help these teams, and the scheduler that is built within Run.ai, how does that help teams manage that precious resource?
Great question. So as you said correctly, GPUs are very expensive. And unfortunately, what we see with a lot of companies adopting Kubernetes for AI is that their GPUs are very underutilized. And the reason for that is that the default scheduler of Kubernetes only allows a static allocation of GPUs, which means that, let's say, each data scientist gets 1 GPU. He can then run jobs on this GPU, whether it's interactive sessions to debug and develop his model, or if it's a train job to train this model. But what we see with data science's usage of GPUs is that it's not something constant. It's not something that you can just put a static quota and it would work. Sometimes, some days, data scientists would want to use a lot of GPUs. Maybe they would have a model that they would like to train on a very large data set, which would require a lot of compute resources. And maybe some other days they won't need any GPUs. So the way that we help with that is, first of all, you see that a job with Run.ai is associated with something called a project, right? Project team A in this case. So if I go to the projects view, you see that a project in Run.ai can refer to either an individual researcher or a team of researchers. And then each of these projects get an assigned quota of GPUs. But this quota isn't a static quota like I just described. We call it a guaranteed quota. What this means is that, let's say, if team A gets a guaranteed quota of 2 GPUs, it means that whenever team A asks for 2 GPUs, the system would make sure that they would get them. However, we would also automatically allow team A to use more than 2 GPUs and go over quota whenever there are free GPUs in the cluster. So if at some given time, team B are not using their GPUs, we would allow team A to go over quota and use all of the 4 GPUs in the cluster. And by that, improve the productivity and the GPU utilization.
And so that kind of begs the question, if you've got multiple teams that have a guaranteed quota built into the system, you are either over provisioning your system in hopes that teams don't collide, or you are under provisioning your system and not making full use of the resource. How do you manage that kind of contention?
Great question. So I think the best way to explain is just to run a few jobs, and we'll see how that works in action.
Great.
So to launch jobs with Run.ai, as we are a plugin for Kubernetes, there are different ways that you can launch jobs, whether it's using our researcher user interface, which I would show in a minute. And we also have a command line interface, and we also have integrations with popular open source tools like Kubeflow, Airflow, MLflow, Jupyter Hub. But again, for the purpose of the demo, I'll just show our researcher UI. So I switch to our researcher UI, and here I can see the same job one, which is already running. I can go to the submit section here and submit a new job. So to submit a job, I can just give it a name. Let's call it this new job, job 2. I can then choose a Docker image that I would like to use for my job. So again, as we are running on Kubernetes, every job would run as a container, and I need to specify the Docker image that I would like to use. So this quick start image is an image that we use for demos. It contains my data science framework, TensorFlow in this case, and it has all of my model dependencies, and it even has my actual Python code and data set all baked into the image. So it's ready to go. I can then choose how many GPUs I would like to allocate to this job. Let's say I want 2 GPUs, and I can then choose the project that I would run this job for. Let's say I want to run it for team B. So I can then just click on the submit button. This would now start a new job as a container on my Kubernetes cluster. And this job would allocate 2 GPUs out of my cluster, and it would start training the deep learning model in this image on the 2 GPUs. So I did see that this job is just started, and we can switch back to the admin UI, and we should see it here, right? So we see that we have the job from before for team A. Team A are using 1 GPU. Team B are now using 2 GPUs, which is, if you remember, they're using all of their quota, right? Because they had a quota of 2 GPUs. They now ran a job that allocated 2 GPUs. So they used up all of their quota. However, we still have 1 free GPU in the cluster, right? We're only using 3 out of the 4. So what I can do is I can go back to the researcher UI, and I can try to submit another job. To make it easy, I can just go to the previous jobs here and run a new job. Let's call it job 3, and use the same Docker image for the example. This time I'll ask for 1 GPU, again for team B. And once I click on the submit button, we'll see that the system will now allow team B to go over quota and use more than the 2 GPUs that they were originally assigned with. So we'll allow them to use 3 GPUs and run an additional experiment. And we see that this job just started running. And if we go back to the admin user interface, we should see here, it's popping up here in a few minutes, a second, sorry. So, just this alone could not have been possible without Run.ai, because the default Kubernetes scheduler does not allow this capability, right? So we see it here clearly. Team B are now using 3 GPUs, going over their quota, running an additional experiment, and we reached a full capacity, full utilization of the GPUs in our cluster.
Got it. And so does that imply that there's an overall constraint that the number of guaranteed GPUs is equal to the total number of GPUs in the cluster at any given time?
Right. It is a good practice to make sure that the sum of all guaranteed quotas is either equal or lower than the total amount of GPUs in the cluster. This way, we can actually make sure that we guarantee, the amount of GPUs that we guaranteed that was set for each of the projects. Now, an interesting question now would be, okay, what happens if suddenly team A asks for another GPU, because they also get a guaranteed quota of 2 GPUs, right? So we have to make sure that whenever they ask for 2, they get 2. But how would we do that? Because the cluster is at full capacity, right? So let's go and actually try to run another job, and we'll see what happens. So we can go and just click on the last job and just click on clone. This will also give us all of these fields already filled up, and I can try to run another job. Let's call it job 4, and ask for 1 GPU and use the same Docker image, but this time let's ask this for team A, right? And if I click on the submit button, what will happen now is that the system will now use the fairness algorithm that we've implemented on top of our scheduler. It will then automatically preempt one of the jobs of team B that went over quota, and then free up a GPU and allow team A to run their job instead. So this will result in a situation where both of the teams are fairly using the GPUs in the cluster based on the quotas that were given to them. So if you look here, you see that job 3 that we started earlier for team B was pushed back to the queue, right? We went from the active job list back to the pending job list, and now job 4 for team A would be able to run instead. And you see this happens completely automatically, no need for any manual intervention. And again, this will result in a status where each of the teams are using 2 GPUs equally, using the GPUs in the cluster. And again, we are at full capacity, full utilization of the GPUs.
In a sense, this is implementing something akin to like a spot instances on a customer's own GPU hardware.
Exactly. Yeah, this is a good point. It's a good analogy. So we will allow you to go over quota, right? And use more GPUs than what you were guaranteed to get whenever there are free GPUs in the cluster. Because, if they're just, GPUs sitting idle, why not let you use them? But, whenever you go over quota, you do need to take under consideration that these jobs that went over quota, maybe if somebody from another team try to claim his guaranteed GPUs, then your job might be pushed back to the queue. By the way, this job that went back to the queue, we don't just delete it and it doesn't just disappear, right? We just we send it back to the queue. We calculate the time that it's waiting in the queue. We save the state of this job. And whenever there would be a free GPU in the cluster, we would automatically resume this job from the last point, the last checkpoint that was saved. So no work would be lost. It would continue whenever there would be a free GPU in the cluster again.
Got it. Now, one of the nuances here is that you could kind of make this assumption that a GPU is a GPU, but in fact, in the real world, data scientists will tune their workloads to specific types of GPUs or have specific RAM requirements or things like that. Does the system accommodate different types of GPUs?
Yes, very good question. And we actually, most of the time, what we see is that companies have heterogeneous clusters of GPUs, because you might, purchase some, let's say V100 GPUs, but then, NVIDIA would release a new version, or, the A100 GPUs, which are faster and stronger, and you might want to get a few of these. And then we allow you on the project configuration options to match the workload type to specific GPU types. So for example, train jobs are very GPU intensive. They would require a lot of GPU power. So we would let the admin, configure it so that every train job for a specific project will always run on, let's say, the V100 or the A100, which are powerful GPUs. But then interactive sessions, which do not require a lot of GPU power, can be matched to, let's say, a T4 GPU. And so we do support different types of GPUs, and we can even automatically, based on the workload type, we would choose, the appropriate GPU to accommodate it.
Mm-hmm. And Kubernetes supports different types of affinitization. Is there a role for node locking or affinity in the data science workloads as well?
Correct. So, if we saw how researchers, submit their jobs, there is also a section here about node type. So for a specific job, a researcher can say, I want this job to run on a V100 GPU or an A100, for example. So the admin can decide if he wants to give this freedom and flexibility to the researcher, or he as an admin wants to have more control, and he would force the researchers based on the workload type that they're trying to launch to use a specific type of GPU.
And it looks like you're inputting freeform text there. Are those freeform tags that the administrator can specify, or are they specific to GPU types that are defined someplace else? Could I implement another type of node affinity based on some arbitrary, internal constraint?
So this feature, node affinity, that we've implemented is based on node affinity in Kubernetes. So prior to setting up these labels here, you have to set the relevant labels on your actual nodes in Kubernetes. We have instructions in our docs on how to do it. It's very simple, and then we also provide, like you mentioned, free text. There is a way, and you can see an example here about, like, these are our user templates. So we allow researchers to create templates with predefined configuration. So then they can save templates for different types of workloads. So it would be easier for them to just run them again. But we also have something called admin templates, where the admin can define a preset list of node types, and then the researchers won't be able to just put in any free text here. They would have like a drop down button, and they would have to choose from one out of three options, or that's also possible.
Got it. Now, going back to the GPU as this precious resource, one of the longtime frustrations for teams is that they get these powerful GPUs and they want to share them, but the standard capabilities of Kubernetes and the drivers don't allow them to use fractional GPUs. And that's something that Run.ai has been focused on for a while. How does that work?
Great question. So you can see on the table here that all of the jobs that we ran so far are train jobs, and train jobs would often run on full GPU or even multiple GPUs like we ran here. However, for interactive sessions, when researchers just want to debug their model, they want to develop their model, they will still want to have at least a fraction of a GPU allocated to their session, so they can run some small short executions, short cycles of execution, just to see that their model is behaving as they expect. And it's a shame to waste a whole GPU on this type of interactive session. Unfortunately, Kubernetes does not provide this capability out of the box, but we in Run.ai developed this, and this is based on some very deep virtualization technology that we built here. So what this allows you to do, and I can just delete a few jobs so we'll have some space in our cluster, and because I want to show you how this works. The most popular, I would say, tool for interactive sessions for deep learning is Jupyter Notebook. So we actually made it very easy in our platform to launch Jupyter Notebooks. And if you remember from earlier, I chose here in the requested GPU field, let's say 1 GPU or 2 GPUs, but I can also ask for a fraction of a GPU, and this can be a third or half of a GPU or only 20%. And this works with any type of GPU. So, we saw earlier, different types of GPUs like V100s, T4s. This would work on Teslas and any type of GPU whatsoever. So a popular use case would be that, let's say we have 3 researchers in a team and all of them want to start an interactive session on a Jupyter notebook and work and debug their model. We allow them to run all of these 3 sessions, for example, on a single GPU, then free up other GPUs for train jobs. So let's run a few of these. I can go and call this new job, let's call it int for interactive, it's int1. And you see, I just turn on this Jupyter notebook flag. And in the image, I chose a Docker image that contains a Jupyter notebook. And I asked for only a third of a GPU. I can submit this job now. Let's go and run another one. We'll run int2 as well on a third of a GPU using the same image. I'll submit this guy. And let's run a third job int3, again with the same configuration. And I'll see that all of these 3 additional jobs would be able to start. We also see the type would be interactive, right, as opposed to train. And each of them would have only a third of a GPU allocated to it. So just to show you, we can go and just clicking on any of these jobs, we see that they already started running. I can just click on the connect button here. And it would just connect me to my Jupyter notebook. So as easy as 2 clicks and I'm inside my notebook, I can go and start running, working on my model. And just to show you that indeed we are only allocating a fraction of a GPU, if I go to the terminal here and I run the NVIDIA SMI command inside the terminal, I'll see that I have only a third of the GPU memory of this Tesla T4 GPU allocated to this Jupyter notebook. So I didn't have to make any changes in my code. I didn't have to make any changes to the Docker image, to any configuration. This would just work out of the box. And what this will result in is you would see that now we actually have 5 running jobs on 4 GPUs. And we have customers running 20 jobs on 4 GPUs or even 40 jobs. So obviously this would make the researchers much more productive. They won't have to wait in the queue and wait for another researcher to finish, debugging his model. We can run much more jobs and much better utilize these very expensive resources.
Now, one thing I might want to do in this interactive scenario is burst and use more of a GPU if they're available, akin to the ability to, I guess, kind of statically create a job with additional, beyond my quota. Is something like that available or something that you're looking at, or is it even something that you get requested for?
Interesting question. So the thing is that we, by design, we decided to allow train jobs to go over quota, right? Because train jobs can run for a long time, a long period of time. They're unattended jobs by design, and they just run to completion. So they can run for hours, sometimes days, and then we can allow them to use over quota any available resources on the cluster. Then we might preempt some of these jobs. We would resume them, and eventually they will all be completed. However, interactive sessions, we don't want researchers to have this, annoying feeling of, you're in the middle of debugging your model, and then somebody, preempt your jobs, and your session just dies, automatically. So because
that kind of bursting would create for a poor user experience.
Exactly.
So you kind of stick to the guaranteed paradigm for interactive jobs.
Exactly. So for interactive jobs, we allow you to run, these jobs only up to your quota. However, we are working on some new and very exciting technology that should be released in just a few weeks, that we call swap. And what this means is, and you can actually see it right now, you see that all of the GPUs are currently allocated but the GPU utilization is not 100%, right? Because these interactive sessions, even though they started, they are at 0% utilization because this is how interactive sessions work. I started an interactive session, it allocated even just a third of a GPU, but currently no code is actually running there and utilizing the GPU. And this is what would very often happen with these interactive sessions, because researchers does not constantly run commands there. They would maybe look at their code, debug, they may go for lunch, maybe then do something else. And sometimes GPUs would just sit idle for a long period of time inside these sessions, and nobody would be able to use them. So that's a shame. So this new swap technology that we're working on would allow train jobs to take these GPUs, without the researchers even knowing them. So let's say we have a Jupyter notebook allocating a GPU, and this, not really actually utilizing this GPU within the interactive session. And then there might be another train job waiting in the queue, actually needing a GPU. So behind the scenes, we would take away the GPU from the interactive session to the train job. We would let the train job actually, use it and train a model on it. And once the developer, the researcher working on the interactive session actually tries to run some code and use the GPU, we would automatically bring back the GPU and allow him to continue debugging his model without him even noticing. So with very, very low performance degradation, not even noticeable. And this would make the utilization even higher and would not require the researchers to do anything. So we would just do this behind the scenes.
Okay. We've talked primarily about GPUs thus far. Is there any consideration for CPUs in this scenario?
Definitely. So we know that even though GPUs are very popular these days for deep learning jobs, some jobs might require CPUs and maybe even only CPUs. So we do show here, you see that we have this analytics dashboard and we show the admin information from the cluster, and these would be metrics that are not only GPU and GPU memory, but also CPU allocation, CPU utilization, RAM memory. You can filter this, for any time range that you want. And also for submitting jobs, we talked mainly about GPUs, but if I expand this resource allocation section, you can see I can ask for, even 0 GPUs, but let's say for a specific job, I can ask for, say, 8 CPUs. I can even limit the number of CPUs that would be used within the job. I can ask for how much RAM memory I would like to use, and I can limit the RAM memory. So you can use, other compute resources as well as CPU and RAM memory, not only GPUs.
Okay, great. Maybe a last question. Looking at this researcher user interface, it allows me to launch one-off jobs, but I may want my jobs to run in the context of a broader workflow or pipeline. You mentioned integration with Kubeflow and Airflow and others. Is that where that comes in? Exactly.
So if we think about, where Run.ai comes in, in the stack, so, the core, value of our platform is that we sit very closely to these hardware accelerators, to the GPUs, and we do, the difficult job of scheduling and utilizing these GPUs better. But we understand that there are a lot of popular data science platforms in the market, and we want to allow researchers to use, their platform of choice. So we decided to integrate with all of these popular data science frameworks. And then, for example, Kubeflow is now getting a lot of popularity. It's an open source project, and just like you said, it provides pipeline capability. So with Kubeflow, you can build automatic workflows called pipelines that can, run a sequence of workloads automatically. For example, get some data, process it, then train your model on this data, then run some verification, then maybe deploy your model to production. And as Kubeflow is also running on Kubernetes, we were able to very easily integrate with Kubeflow so that every step within the Kubeflow pipeline will actually be scheduled using the Run.ai scheduler instead of the default scheduler of Kubernetes. So then you can just use Kubeflow as your interface instead of using, our user interface, but you would still see the jobs, that you launch from Kubeflow showing up here in the admin UI. They would still, the Kubeflow pipeline jobs would still be taken under consideration with the quotas and priorities and everything that were set here. You would be able to go over quota. You would be able to run on fractions of GPUs. So you would get, the same capabilities, the same functionality, just, use a different interface, Kubeflow for that matter.
Awesome. Very cool. Very cool. Thanks so much, Guy, for a great demo.
You're welcome. Thanks for having me.
Thank you.